would contain a subsequence. So now, think of y1 as an entry of this subsequence. Think of y1 as an entry of this subsequence, right? So think of y1 as one of the terms of this subsequence, right? y1 as one of the terms of this subsequence. So suppose for the sake of argument, this subsequence is contained between 0 and half. For the sake of argument, suppose this subsequence is contained between 0 and half, and y1 belongs to 0. Now think of breaking 0 and half into two subsets. Yeah? Okay. Now, because this interval, this set contains the subsequence, one of the two sets must contain the subsequence. So suppose this subsequence is contained here, say 0, 1 by 4. So let y2 be a term of this subsequence. Then I break this down into 0, 1 by 8 and 1 by 8, 1 by 4. And by the same argument, one of those intervals must contain the subsequence. Suppose 0, 1 by 8. So you call it, say, y3. So you get the sequence y1, y2, y3 which has the property that the corresponding elements are getting closer and closer and closer together because they're lying in smaller and smaller and smaller. Right? So we have a sequence which satisfies the Cauchy property. That is, elements keep on getting closer and closer and closer together. Which means that this subsequence will be a convergent subsequence, because we know that whenever a sequence, elements of a sequence have the Cauchy property, that is the distance between the two elements keeps on getting closer and closer and closer, in R the sequence converges. Right? Okay? Sure? Right? So this is essentially the Bolzano-Weirstrass theorem. Right? In R1. Now, suppose I want to generalize it to Rn. What will you do? Suppose I want to generalize it to Rn.
So what if both 0 and half and both and
Look, we have a sequence, right? Let that sequence be 1 upon x. Okay? Let that sequence be 1 upon x. Right. Now, I can always think of a subsequence 1 upon 2x. Right? Okay? So what are the terms of 1 upon x? 1, 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, 1 upon 6, etc. What would be the terms of 1 upon, so what would be the terms of 1 upon 2x? Half, 1 by 4, 1 by 8. All these will lie between 0 and half. The sequence lies between 1 to 0. I can always think of a subsequence 1 upon 2x which lies between 0 and half. Right? Sure? So basic point is lie either in this interval or this interval. Whatever interval lies in, I can always split it into smaller intervals. And I keep on doing that, so the subsequent terms keep on getting closer and closer together. Yeah, it can lie on both, meaning, so basically, what did I mean by lying on both? Because I broke it into 0 and half. But suppose my 0 and, so I could always break it into two parts. I said both because I used the 0, half, half one. But I can always think of a subinterval. which is not necessarily symmetry. It is not necessarily say I can think of 0 to 3 by 4 and 3 by 4 to 1. Yeah, in such a way that one of the intervals contains this fully. Right, just for the argument's sake, just to illustrate the point to you. Right, so basic point is we can then get these subsequences into smaller and contain into smaller and smaller intervals so that their corresponding elements are getting closer and closer together, which is the Cauchy property, so that eventually the sequence subsequence converges. Now we want to generalize it to Rn. अभी कैसा करें? Now we are going to look at that textbook. We are going to evolve our own ideas. So first, how do you conceive of a closed and a bounded set in Rn? So what is a closed and a bounded set in a two-dimensional space? Say for example, this is y, this is x. Yeah? We are thinking of a set of points which have a length less than, say, some number b. Okay, so what would such points be? How will you draw this area? Set of all points which are at a distance, think of all vectors that are at a distance less than b from the origin, less than or equal to b from the origin. Circle, right? So if you took a circle, it's supposed to be a circle, okay? Radius b, right? Circle of radius b will be a closed and a bounded set in R. Right? Okay, circle of radius b will be a closed and a bounded set in R. Right?
We are considering it as an absolute value.
No, length and length is absolute number. Length is absolute number. So all points, even if we think of a vector here, this vector will be say minus x minus y. Right? The length is still an absolute number. No? Set of all points in the distance less than b, less than or equal to b, will be an interval including the boundary. If I said less than b, then I would not get the boundary. Then it would be a circle which never ends, but which is still at a length less than b, which is still at a finite distance from the origin but never gets over. Right? Yeah? You see the point? See, this sometimes runs very, very counter to our intuitions. Right? Because think of a snail which is walking across every point. So think of an open. So I will draw a circle here. Suppose this is supposed to be an open interval. I am looking at the set of all points which are at a distance less than, say, b. Right? Less than b. And I have a snail which starts from here. And the snail is supposed to cover every point on this radius. Is this distance finite? Yes, it is finite. But will the snail ever be able to reach the boundary? It will not, because you have to cover every point and there are infinitely many such points. Yeah? So the snail will never be able to cover that finite distance. Sure? Because it needs to cover every point. Okay? Fine. So, on the other hand, if it's a closed set, then the snail will reach the boundary at some point. It might actually not, but there is actually at least somewhere where it ends, less than b. Right? So it includes the boundary. Right? It includes the boundary, less than b. Sure? Less than or equal to b will include the boundary. So think of such a set which includes the boundary, the circle including the boundary. How will a set in R3 look like? A closed and a bounded set in R3 looks like a sphere along with the surface of the sphere. Everything inside the sphere and the surface of the sphere. Right? Okay. Now, so intervals in Rh will be some such objects. How will you define interval? How will you generalize this proof to Rm? कैसा करेंगे? इधर अपन ने क्या किया सोचिए? ये क्या था? ये लेंथ था ना, इसको अपन ने दो में ब्रेक किया ना. So basically what will be a sequence in Rn? It will be vectors. X1 will be an n-dimensional vector, x2 will be an n-dimensional vector, x3 will be an n-dimensional vector, x4 will be an n-dimensional vector. So, right? Think of a sequence of such vectors in some kind of a sphere in a three-dimensional space. Right? Okay? Sure? It will have a subsequence. So suppose instead of this, suppose you think of half the ball. The subsequence has to be either here or here. Suppose it lies here for the sake of argument. You can cut this ball even smaller. So cut the ball even half. So that it lies either here or there. Then you make it even smaller. So basically what you're going to do is, what you did to the interval, you break it into half. You keep on breaking this ball into, you keep on shrinking this ball by half every time. Yes, to make it half the size of the ball. And that's how your argument essentially would go in an n-dimensional space. Right? Okay? As long as your example is concerned, even if you remember the R1, I am fine. Then how to do it in R1, the one-dimensional real space, then we have the Bolzano-Weirstrass Theorem. But as long as you know how to generalize it, because only the terminology is going to change. I am to write less than b, then you are going to say, instead of that you are going to say b by 2. Think of all points there less than b by 2. Then you are going to say b by 4, b by 8, and like that you are going to do. Right? So, sorry, as long as you see the inside here, I am fine. Yeah? Clear? Okay. Now we
So what is the sequence is contained in both of the
no. You can always think of a interval, sub-interval. A smaller interval which will contain the subsequence.
So but the subsequence is contained in either or both of the
No. Both meaning, because I have defined it here like this. But I can always redefine my sequence in such a way. Like I can make say 3/4 of the ball and 1/4 of it. Then I can keep on. The point is I was able to keep on shrinking the ball. So the points keep on getting closer and closer and closer together.
So we can change the subsequence from the sequence xn so as to fit it into any small size of the.
No, so you have a sequence x, right? So what is the point? The proof says that every sequence in a closed and a bounded set will have a convergent subsequence. What do you mean by convergent subsequence? The set of elements in that sequence will get closer and closer and closer. So if the sequence is numbers, you want a subsequence whose elements keep on getting closer and closer and closer together. That is, they keep on lying in smaller and smaller and smaller intervals. Or they keep on lying within smaller and smaller spheres, which you keep on shrinking. Right? Okay. So point is, if there is a sequence on this interval, I can always think of a subsequence and suitably break this interval in such a way that it contains the subsequence. Now same logic applies. I can break this interval again, which is a subsequence, into suitable parts which contain the whole subsequence. Right? And I can keep on doing this, right? So think of the terms, the first term will be contained in the first set. Think of the second of the sequence which is contained in the second shorter intervals. Think of the third element of the subsequence which is contained in even shorter interval. So eventually the terms will keep on getting closer and closer together, which is the Cauchy property, which means that the sequence will be a convergent sequence. Right? Sure?
A distance b which can be reduced to.
No, see, it's a closed set. So there is, by definition, there is a distance b. So there all points are less than that distance b. All vectors are contained in a sphere of a length of a radius less than or equal to. But what we say is, if you take such a sequence, then that sequence you can always find a subsequence which is contained in a smaller b by 2, b by 3, whatever. Right? And then, so So think of an element of that subsequence which is contained inside V1. If I make V even smaller, I'll find another element of the sequence. I can keep on subsequence. I can keep on making these smaller and smaller and smaller, which means that the terms get closer and closer and closer together. Right? That's how one proves the Bolzano-Weirstrass theorem. Right? That's how one proves the Bolzano-Weirstrass theorem. Now we come to something interesting. Okay, we now come to something interesting. Okay, so applications of the Bolzano-Weirstrass theorem will come sometimes later. This is a very important theorem on ideas to do with intermediate value theorems and many other theorems that we are going to use later. So it's a kind of a theorem which is going to be used a lot, especially if you do a little bit of higher kind of microeconomics. Then the Bolzano-Weirstrass theorem will be very important in proving generally. For example, it's very important theorem in proving the existence of a general equilibrium. Right? So we'll do that when we come. But just remember what so everybody knows what the Bolzano-Weirstrass theorem is? Tell me what the Bolzano-Weirstrass theorem is without reading what you've done. Think of a closed and a bounded set in R or Rn. Think of any arbitrary sequence in R in that closed and bounded set. By the way, closed and bounded sets in Rn are called compact sets. So any arbitrary sequence on a compact set will have a convergent subsequence which are converging to R. Every arbitrary sequence on a closed and a bounded compact set in R or Rn will have a convergent subsequence. That is the Bolzano-Weirstrass theorem. This one line, and you know how to define it. How to prove that? It's not really very difficult. Now I'm going to talk to you about matrices. Right? What's a matrix? You see? Yeah, what did you say?
Collection of elements in rows and columns.
Okay. Any other idea of a matrix? Any other idea of a matrix? A little louder. Combinations of rows and columns. Anything else? Yeah? Any other definition of a matrix? Any other idea of a matrix? Can you tell me? I am trying to find the right thing. Yeah? Linear functions. So let's first come to the idea of a linear function. So think of a linear function in general has the property and so it has the property and so for example, if you think of the expected value function, what is equivalent to expected value? It's a classic example of a linear function. Expectation of x plus y is expectation x plus expectation y, right? And expectation of alpha x is alpha expectation x, Right. Now think of a random variable, so you are tossing a coin or rolling a die. For example. What are the possible values that a random variable can take? 1, 2, 3, 4, 5, 6. Right? Okay? What are the various probabilities that it can take? Let's say 1 by 6, 1 by 6, 1 by 6. Right. So think of the vector P as 1 by 6, 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 1 by 6. Right? Think of the vector X as 1, 2, 3, 4, 5, 6. Right? So what is the expected value? P dot X. The dot product of P and X. So it is P1 into X1 plus P2 into X2 plus P3 into X3, so on. Right? Or in a matrix formulation, what would that be? So if X is a 1 row 6 column, yeah, P dash will be 6, P dash will be, so P dash will be, so let me write this. So I write this X dash P dash, when P will be a, P dash will be a 6 rows 1. And you get a 1 cross 1, which is really XP, X1 P1 plus X2 P2 plus X3 P3, etc. Right? So what is an expected value? It's a function. So if you think of X1 and P, right, where there are 6 possible values that X can take, right? So you can think of a 6-dimensional space, 1 for each value, right? So X is a point which takes 1 on one axis, 2 on the second, 3 on the third, 4 on the fifth, 5 on the sixth. And P again takes 1 by 6 on the first axis, 1 by 6 on the second axis, 1 by 6. So, but P dot X is a single number, expected value X. So what we have is a function from R6 to R1. The expected value operator is a linear function. Yeah, expected value operator is a linear function from Rm in general to R1. Right, for a discrete random variable. Is the variance a linear function? Is the variance a linear function? Is the variance of x plus y variance of x plus variance of y? In general? No, because there is a covariance term. Yeah? Similarly, is variance of alpha x alpha variance of x? Is variance of alpha x alpha variance of x? Is alpha square variance of x? So it's not a linear function, right? Okay? But the expected value operator is a classic example of a linear function, right? Okay. Now think of. Okay, let me take a simple example. Okay. Think of a function from say R3 to R1. Okay? Think of a function for an R3 to R1. Okay? Right? Now, what is R3? R3 will be some vector. Say x1, x2, x3, so you'll have an x-axis. So let a point on x1, let a point on x2, let a point on x3. Right? Sure? Now, we know that each of these points, okay, so when I think of a two-dimensional space, yx, think of a point 2, 3, right? Okay, then this point 2 can be written as 2 into 1, 0, 1 on the x-axis, right? Okay, sure. Similarly, I can write this point as 3 into 0, 1. This will give me the vector 2, 3. The vector 2, 3 can be obtained by 2 into 1, the vector 1, 0. plus 3 into the vector 0, 1. Sure? What is the vector 1, 0? 1 here, 0 here. What is the vector 0, 1? Right? Okay? So the point is, every vector in this space can be represented as this vector into some constant plus this vector into some constant. For example, how will I write the point -7, -20? If I want to represent a vector -7, -20, -7 into 1, 0 plus -20 into 0, 1. So every point, in any point in this whole space, can be represented as the first vector. I'll call this E1, which is this E2, which is this, right? E1, E2 is called the canonical basis for R2, right? E1, E2 is called the canonical basis for R2 because every point here can be represented. In general, you can have many bases, right? I can just turn the whole axis around at 90 degrees and some other point, right? But the usual one is the 0, 1, 1, 0. So it's called a canonical basis. Similarly, in R3 there will be a canonical basis. What is the canonical basis in R3? 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? In R3 there will be a canonical basis. So think of such a canonical basis in R3. Right? So therefore, our vector now x1, x2, x3 can be written as x1 1, 0, 0 plus